Right. So the CHSH inequality is very easy to test and it holds a lot of utility. And the point being, the entanglement-based quantum network, its goal is to get any parties on the network entangled. And that entanglement is typically, in many cases, just bipartite two-party entanglement. So when you get those two parties entangled, you just need to apply the CHSH inequality and you can test the end-to-end entanglement. Now you could apply CHSH inequality to any of the entangled states in the network. So throughout your whole distillation, production, distribution processes, there's all these places that you could apply it. But at the end, the most meaningful place to apply your test is on the entanglement produced at the end nodes. Now, as I showed, that there's all sorts of ways that you can expand upon non-classicality. You can look at different entanglement topologies. You can look at different network structures, and you can add signaling in. And all of these will make it more complicated to derive classical bounds. And in many cases, the classical bounds become very, very difficult to solve at scale for large systems. Another challenge that arises in large systems is sometimes even calculating the quantities or the probability distributions cannot be done in any sort of efficient time and cannot scale because you simply cannot measure enough data in a reasonable enough time to witness the resource. So that said, the best test that we have right now is a CHSH inequality. It's very, very simple, and it has a whole bunch of utility because it can test that end-to-end entanglement. So moving forward in certifying quantum resources and networks, the simplest tests are going to be the best. However, there do exist example tests that can be used to do much more complicated scenarios, such as complex entanglement structures or complex network topologies that the CHSH inequality simply cannot witness.